Well, hello, everyone. My name is Jamie Rosen. I am the chair of the D Foundations Institute Information Management Systems Committee, and welcome to our Diving Deeper into Data webinar series. I'm very excited about today's webinar because it's a topic that I'm not very familiar with, so I'm hoping to learn a ton. Hopefully you can see the presentation. I apologize, we have an internet outage in my region, so I've just switched to my phone. I have a limited view of what you can see, but I'm excited nonetheless. So our speaker today is JJ of Langan Engineering. He's been a member of our Information Management Systems Committee for a while, and we're looking forward to his participation as really our remote sensing representative. And today's talk will be on a very interesting new and current remote sensing topic of InSAR. Great.
I was able to move it back, so
yeah. Yeah, sorry for the awkward start. I'm hoping for internet any minute now. So hopefully you saw this. If you do have questions, please put them into the question box that you should see. And I'll pass things over to my friend JJ. Good luck.
Thanks, Jamie. As Jamie mentioned, I am Jagrat Jariwala. I go by JJ. I want to quickly thank Jamie for putting all of this together, and then Jamie and Angelina from DFI for all the logistical coordination. And I did not realize how much goes into coordinating such webinars. Now, so without further ado, let's get started. Challenges of sharing, visualizing, and interpreting InSAR estimates. So before we, next. There you go. Before we dive into the presentation today, I wanted to quickly get a sense of how familiar are folks with InSAR. First, so if you can take 30 seconds maybe to respond in chat and let me know 1 through 4 numbers. 1 being very familiar, 4th being not so much, just heard about InSAR and remote sensing, seemed interesting, so join the call. Or in between, wherein you have seen it getting used, or which is number 2, or 3rd, have not heard about or have heard about it, but not seen it in action. So if folks can just take a minute here, and now I'm trying to pull up the webinar chat. If you can take 30 seconds to respond, that'd be great. There you go. 1, I see 3, 4. All right, a few 1s. See a couple of 3s. 1, 4. All right. So a good mix. Seems like a lot of people have heard about and used InSAR, so that's great. All right, so I know how to modulate the presentation a little bit now. So all right, let's go ahead then. So today, the way have structured this presentation is we're going to talk about underlying technology for folks who answered 3 or 4, and then talk about a bunch of applications wherein folks have used InSAR very effectively. And then key considerations, things that folks need to keep in mind while using InSAR. So underlying technology. What is InSAR? InSAR is an abbreviation for interferometric synthetic aperture radar. The SAR aspect corresponds to the satellites, usually moving in polar orbits, north to south, south to north. They capture data, and that data is then processed through this process called interferometry, which essentially converts this SAR data into millimeter level movement estimates. It is this property that is very relevant for civil engineers. So very quickly, what InSAR does, and very simplistically do that. InSAR captures images of your area of interest. It irradiates the area of interest with certain kinds of waves, then captures the reflections using the sensors on the satellites. It typically gets phase and amplitude data. Amplitude data is useful for quality purposes, but phase data is the key for it performing interferometry. InSAR does it. Let's assume. Oh, just saw the text message from Jamie. Okay, let's continue. Let's assume that the capture happens at time t, and then again at time t plus delta t. InSAR tries to figure out how long did the reflected waves take to get back to the sensors. It utilizes this property to come up with movement estimates. One key concept to understand here is the movement estimates are movement estimates in the line of sight. The satellite looks at the area of interest at an angle, and so the movement estimates are also at that angle. One other key concept for utilizing InSAR is its process of capturing ascending as well as descending imagery. Just by the virtue of Earth rotating on its own axis and these polar satellites, SAR satellites, moving in north to south and south to north directions, it captures the same area of interest while traversing in ascending orbit, so that is south to north, and traversing in descending orbit, north to south. So in reality, if your point of interest moved by this vector d real showcased here, in ascending imagery, the registered movement will be descending towards the satellite, and in descending orbit, it will register movement away from the satellite. You can use these two estimates to then come up with your d real actual movement estimate. Now, for successful InSAR implementation, there are 4 key steps. First is acquisition of all this imagery. Second is performance of interferometry on that imagery to come up with movement estimates. Third is sharing and visualization of those estimates. And then fourth, evaluating and drawing conclusions with respect to the civil engineering problem at hand. In today's webinar, we are going to focus on steps 3 and 4, which are more relevant to civil engineers. So what is the fuss about? Now you have an ability to get something like this. For folks who have not seen InSAR estimates before, these green, yellow, red dots are movement estimates. The red dots are movement away from the satellite, generally settlement. Green dots are movement estimates of that asset, which are generally stable. Blue dots are movement estimates towards the satellite, which represents upheave. These are all color coordinated, and this is the scale that you're looking at. In terms of point density, you are able to get 100,000 point estimates in 1 square kilometer area. That's the density. I guess I'll give you a second to wrap your heads around that. 100,000 point estimates in 1 square kilometer area. So gone are the days wherein the question was, how can I find enough data Now, the question is how to parse through these gigantic data sets to get to the relevant information. The other thing to keep in mind is InSAR has the ability to go back in time. There is already historical imagery available that can be leveraged to come up with movement estimates that we just saw. The historical imagery goes generally for the Earth goes back to 2015-16, and there are certain areas wherein you can get imagery as far back as 1990s. Now, for Earth observation geeks, the NISAR mission's launch date is Q1. It's going to be in the Q1 of 2025. The folks who are not familiar with NISAR, it's a NASA and Indian Space Agency collaboration project, wherein now certain satellite imagery, which was very expensive, L-band imagery, which has capacity to penetrate vegetation, is going to be available for free once this gets functional. In my mind, this is going to revolutionize InSAR for civil engineering applications. We'll see, fingers crossed. Now, in terms of applications of InSAR, there are three major industries wherein it has been used and leveraged quite a bit. The first is mining industry. By far, the penetration of InSAR in mining industry has been tremendous. Much better than the oil and natural gas and civil engineering industry. They have used InSAR to monitor bench slopes. I've also helped folks utilize InSAR to monitor their other assets, such as tailing storage facilities, such as ash ponds, other leach pads, things of that nature. They have combined InSAR with other Earth observation processes and came up with and utilized that information to understand if there were leakages, if there were breakages in their underground pipes, so on and so forth. Then comes oil and natural gas industry. They have used the property of surface movements, perform model inversion of their reservoir models to better understand how the reservoir is functioning and to get efficient drilling processes in place. Now, environmental compliance for drilling purposes has also started leveraging InSAR. And then civil engineering applications. We're going to go through that a little more in detail, go through all of these one by one. So I have used InSAR for planning of on-site investigations. This is especially useful if the construction, is going to happen or the proposed site is stabilized mine site or landfills. The typical approach is within the building footprint or structure footprint, get as many borings or CPTs as possible and use that information to design your jobs. Now, imagine if you have an ability to go back in time, understand how much the surface moved, and utilize that information. Now, for mine sites or landfills, geotechnically speaking, what would result in settlements is some combination of what kind of material was filled, how much compaction effort was applied to that material, and how deep were those excavations or how deep are the fill depths. Now, if you get information such as this, wherein you can combine areas, for example, quickly put together this visual, the green area moves at quarter of an inch. You can come up with certain density of investigation locations. If then yellow areas which are moving at higher rates, you might want to increase the density there. And then certain localized areas which are just moving too fast, you might just want to avoid constructing any new buildings or new structures on that location. I've used it for a lot of solar fields where such information becomes very useful and folks want to construct on stabilized mine sites or landfills. The other civil engineering application is tunnel construction. Now imagine you have historical information and you can come up with baseline movement estimates of buildings and structures in the zone of influence of your proposed tunnel construction. And now you already know which buildings are moving faster, and you can now modulate the on-site and more conventional monitoring so that those things are captured. There has also been a study wherein folks found the actual zone of influence was much larger than previously assumed. And now the benchmarks of the survey control points were even moving. Now, if that happens, the results are the movement estimates from those systems are biased. And at that point in time, folks use InSAR to back calculate actual movement estimates. Now, monitoring slopes. That's a very similar story here as well. InSAR's penetration in monitoring and providing solutions for landslides and unstable slopes is also quite high. Folks have used InSAR to figure out the actual extents of the landslide, then use that information to figure out where their inclinometers, let's say, are going to go on-site instrumentation. And then I've used InSAR for monitoring slopes and use it as a force multiplier for other conventional monitoring, spatially as well as temporally. Get more estimates, more dense estimates spatially, and can get more frequent estimates and reduce the cost of your conventional monitoring. Access agreements. In urban areas, especially, I've leveraged InSAR when these access agreements are getting negotiated, and folks do not have the ability to install these survey control points or vibration monitors in the neighboring properties. Imagine a case wherein you have baseline movement estimates and then can monitor those neighboring structures over a period of time. Now, if you don't have a very good relationship with the neighbor, these kinds of things come in quite handy. Then construction dispute resolution. It's InSAR's ability to go back in time. You juxtapose that with civil engineering understanding of how or why certain kinds of movement happens. That becomes a very potent force. We're going to go through one quick case wherein construction dispute cases were settled using InSAR. So this is a case wherein the pavement started settling and cracking. The pavements of the bike roads, the pavements, the sidewalk, as well as the roadways, everything started cracking, and a lot of complaints started happening. And the local government officials wanted to use InSAR to figure out what was going on. They didn't know that there was an active construction site which was dewatering, but they were not able to make connections. Now, for folks who have not utilized InSAR before, this is the image on the left is a typical viewer using which you will typically visualize InSAR estimates. All these points are movement estimates. Those are color coded. The red being movements away from the satellite, green for the points which are stable, and blue which causes upheave. These estimates were performed for a period of 2016 through 2021. Here, the red outline is the outline of the construction site where dewatering was happening. The blue circle corresponds to the area of using which the point estimates using which the right-hand side graph was prepared. This graph is displacement versus time series. The construction dispute happened in 2021. Folks started complaining about payment settlements in mid-2021. So using InSAR, folks were able to go back in time, figure out how much the baseline readings were, movement estimates were, which you can see are nothing. And then suddenly there is an acceleration since middle of 2021. For folks who are SI unit challenged, this is a little more than 3 inches per year worth of movement. Now juxtapose that with the understanding that the dewatering started in the middle of 2021. With that, the conversation with the contractor to stop with dewatering becomes really easy. Now, using InSAR, you can come up with visuals like this and understand how the dewatering, what was the influence of dewatering and how much accelerated movement it caused. The conversation about damage claims also becomes relatively simpler when you leverage InSAR estimates. Now, let's talk about some key considerations for leveraging InSAR, things that folks need to keep in the back of their mind. I've divided it into 4 big boxes. Let's talk about planning first. The first being expected movement estimates. Depending on how much movement the area of interest is expected to move, how fast is it supposed to move? Depending on that, different configuration, different wavelengths different waves corresponding to different wavelengths could be a better fit. So that conversation needs to happen right at the beginning between the civil engineer and the InSAR engineer. Other area of interest considerations. Are you trying to monitor an urban area with lots of buildings? Are you trying to monitor a slope which is vegetated? Different type of wavelengths and different types of configurations will be suitable for different applications. So that information also needs to be ironed out at the beginning of InSAR implementation. Then monitoring frequency. With certain constellations of SAR satellites, folks can reduce the revisit frequency. Revisit frequency is just jargon of how frequently you are going to be able to capture the area of interest. Those can be different based on how many constellations are in that particular type of satellites. I have utilized InSAR and leveraged InSAR wherein folks wanted to have a lot more frequently monitored areas during the month of monsoon and spaced out relatively far apart during the rest of the year. So those conversations need to happen right at the beginning. Then cybersecurity. It goes without saying in this day and age, the folks you partner with they should have compatible cybersecurity procedures in place. Questions like, are their employees also using two-factor authentication? Are there enough trainings in place to avoid phishing scams, so on and so forth? Data backup procedures. InSAR, the processing as well as the visualization is very data heavy. So just understanding how these estimates are going to be visualized and what kind of backup processes are in place becomes very critical. So those compatibility items need to be discussed and worked on right at the beginning. Now, a small plug for our committee here. IMS committee has put together this data management guide specification, which is a tremendous resource for any application which is data heavy, especially. Gives you a good edifice on which you can put together your specifications and think about how to leverage these data heavy technologies. Now let's talk about key considerations from the sharing point of view. So static versus interactive way of sharing data. When InSAR, I've seen InSAR being visualized in static ways in a PDF report, a document report with movement estimates, just a quick visual. And then GIS-based viewers, wherein you can parse through the data, understand how different areas are reacting, visualize it in different ways. I strongly recommend folks to use an interactive tool to leverage InSAR. It brings along a lot of value. And we're going to talk about it later on in the presentation. File format compatibility. In terms of how these are shared, sometimes civil engineers would want to visualize all the InSAR estimates with other contextual data, such as where the area of interest locations are, asset locations within that area of interest are, historical failure locations, so on and so forth. And they could not pass it along to other folks for confidentiality purposes. So if they want to visualize InSAR estimates on their systems, on their platforms, they need to understand how compatible different file formats are and how the InSAR engineer is going to process the data would give the processed output. Then training. Training is a unique and an interesting aspect when it comes to InSAR. The InSAR engineer needs to understand how or what the civil engineering application is. If they understand that, the processing of SAR imagery can be done much better. And the civil engineer needs to understand how the processing was done to have better confidence on the InSAR estimates. Now, let's talk about visualization. Key things to keep in mind. First is colored dot plots. I briefly touched upon this, but you really do not want to look at a graph just similar or any visuals just similar to that. You want to be able to click on each of these point estimates and understand how those points behave through the time period during which it was analyzed. Folks might want to run cross sections through the data sets to understand how differently different areas evolve. Those kinds of things are very important when folks are trying to draw conclusions for their civil engineering applications. The other thing is to be able to perform all kinds of statistical functions. If you want to understand how much on an average a particular area moved, if you want to understand just in terms of how different points within the selected area moved. Those kinds of things should be visualized. The viewers or the platforms used to understand and visualize this data should give access and capabilities for that. Ability to filter. In a lot of cases, folks would want to understand how the different areas move. For example, how the buildings moved as compared to how the pavements moved. The case that we spoke about, wherein the government officials were able to correlate the groundwater extraction with the pavement settlements, they also wanted to understand if there were any damages that they would expect on the buildings. The buildings were founded on deep foundation elements, and the pavements were sitting on subgrades. Now, if you are able to visualize point estimates on the buildings separately and point estimates on the pavement separately, you can answer that question very quickly. And that's what happened in that case as well. Then 2D and 3D visualizations. 3D visualizations are always better, but excuse me, those are very data heavy and are expensive more often than not. But for area of interest, which are in urban areas, or if you're looking at slopes, 3D visualizations do bring in substantial value in understanding where the estimate is, how it is all reacting, and how to draw conclusions for your civil engineering problem. Now, visualizing other relevant information. So I've used InSAR for slope stability purposes. And very similar to this, there was a utility, an underground utility in very close proximity to the slope. And folks wanted to understand and make sure nothing's happening near that utility. So visualizing that becomes very critical. Then other surface disturbance locations. Now, if the surface changes during the period in which InSAR estimates or interferometry is performed, then the estimates in those areas are not very representative of what's going on the site. So you want to know which estimates you can be confident about and which estimates you should generally discount. Then recent failure locations. So I've utilized InSAR for sinkhole predictions. And visualizing historical sinkholes helps in understanding what are the typical patterns that would form right before a sinkhole formation. And it also gives you an understanding of where to monitor those well, and if there were any remedial measures, where those remedial measures were performed. Then this GPS location is a stand-in for any other conventional monitoring that you might have. Survey control points, inclinometers, all those kinds of things. You want to be able to visualize where spatially those are. And also, if folks are able to visualize the actual readings with InSAR estimates, that gives enormous value. Other specific areas of interest, future developments or things of that nature. You want to use all of this information, contextual information, when you're visualizing your InSAR estimates. That combination is what makes InSAR very important. Now, there are a lot of processes that goes into converting the phase difference that we spoke about earlier the interferograms into displacement maps. And intermediate steps plus what went into it, for example, digital elevation model that was used to use in the interferometry, plus anything that would talk about how good the data was and how things were processed should be visualized and looked at in conjunction with the actual movement estimates. Now let's look at interpretations. Now you have all this data visualized. What are some key points that folks need to have in mind while looking at all of this? So InSAR is relative in time and space, meaning for the time period that you evaluated movement estimates, the first estimate is going to be a zero estimate, and all the subsequent movements would correspond to that zero estimate. So many millimeters movement from date X, which is the first estimate. It is also relative in space. What I mean by that is InSAR estimates are movements as compared to other assumed stable points. So things to keep in mind are if your reference points are within the area of interest, then your movement estimates are going to be biased. The other thing to also keep in mind, if you're putting your reference points outside, but they are still within the zone of influence and are moving and are not stable, that will also bias the movement estimates in your area of interest. So you want to keep those far apart and on areas or structures which are stable. Now, you saw this visual just a couple of minutes ago, but let's drill down on this. So InSAR engineer would require a digital elevation model to process the interferograms, the phase difference. Now, the InSAR engineer needs to understand if there were any surface changes that happened on the site. So the civil engineer needs to communicate and be on the same page with respect to what digital elevation model was used. Is it latest and the greatest? If there were small areas where filling was done or excavation was performed, which would change the surface, that needs to be communicated to the InSAR engineer. And then InSAR engineer uses assumptions to work with atmospheric and just inherent satellite imagery noise. Those need to be communicated to the civil engineer to understand how confident folks can be with the displacement maps and movement estimates that InSAR engineer comes up with. Then we spoke about ascending and descending orbits and how the same area of interest is looked at during the satellite's movement from south to north and north to south. Now, the angle in which the satellite would look at the structures are different. So in ascending orbit, the one on the left-hand side, the line of sight is due east. And because of that, movement estimates on the western portion or western face of the building are going to be visible, and estimates can be formed on the western face. Plus the roof. The roof is the common factor in both ascending and descending. And in the descending, similarly, the eastern face is where folks will be able to come up with movement estimates. Now, if you are using this to ground truth data and you're survey control points, let's say, or your GPS points are on one of the faces, then comparing the total movement estimates are not comparing apples to apples. The recommendation here is to convert your movement estimates from conventional systems, such as your survey control points or your GPS points, and project it to the line of sight axis and compare those to understand how good of data or how accurate are your InSAR estimates. The conversation is different for the roof, where both ascending and descending are available, and you can then come up with the detailed movement that we spoke about earlier. The other aspect of InSAR is there are areas which are going to be shadowed by structure in between the satellite and the area of interest. So in this case, if you are trying to monitor building B using ascending imagery, and there is a bigger building, much taller building, building A in between, then you won't be able to come up with any estimates, excuse me, on building B. So when you're looking at the InSAR estimates and you don't find any movement estimates on certain buildings, then this process or this shadow effect should be considered. This is also useful in the planning aspects, wherein you want to make sure the important areas of interest are covered one way or the other. In this case, the ascending will not be able to come up with any movement estimates on building B, but descending would. Now, key differences when you compare InSAR with other conventional systems. So first, we spoke about InSAR and its relative nature. It's relative temporally as well as spatially. The second item is InSAR is probabilistic in nature, while, for example, your survey control points are going to be deterministic in nature. What I mean by that is when I'm looking at InSAR estimates, if a lot of points are showing movement, then that gives me a lot more confidence that the movement in that area the movement estimates are representative of that particular surface. Then analysis paralysis. With so much data at hand and so much visualizations that folks would have to do to come up with to get better value, there is a tendency to just get lost in data. So folks need to put together mental models to evaluate. It just takes a little time, but it's easy to get there. The logistical challenges. The first being monitoring frequency. Now the satellite is going to look at the area of interest only so many times and at so much frequency. Now, if you have a case wherein let's say, vibration monitor gives you a threshold exceedance, and now you want to monitor your structure, you would not be able to get let's say, a surveyor on site and get it all monitored. It's not going to work in the same fashion with satellite imagery. It will come and look at the site whenever it gets above that area of interest. The shadow effect that we spoke about, folks need to keep that in mind while choosing the area of interest and the InSAR satellite configuration. and also factor that in during ground truthing. And lastly, when done right, InSAR can be a formidable tool with gives you ability to go back in time and have these gigantic data set and become a force multiplier in terms of movement estimates. The first two steps in successful InSAR implementation that we spoke about are necessary, but not the sufficient case for InSAR implementation, successful InSAR implementation. You need folks who understands InSAR a little bit better and to leverage it fully. And then lastly, visualization capability and contextual understanding of the problem are going to be key for successful InSAR implementation. So with that, I'll conclude the presentation and open it up for questions. I see there are a few questions, okay. Question. Oh, these are comments. All right. So folks,
Hi, JJ.
Hey, Jamie.
We actually have no new Q&A, so I hope people will take a moment to digest all this and add questions if they like. I'll say that was by far the best InSAR 101 I've ever come across, including several presentations, specifically at DAMS conferences. So thank you for that comprehensive and very easily understood introduction. That was fantastic. It should be required of certainly anyone on our IMS committee. So very well done. I'll throw
Thank you, Jamie.
thank you. A few questions at you to get started as give people more time. I really appreciated the list of applications. You know, in Deep Foundation, some of us are pretty hyper focused on civil engineering and a very specific corner of it. So it was great to see, you know, references to property disputes and interesting things. Are there any upcoming applications or even applications you can imagine that might come in the next decade that we should be on the lookout for this very diverse and probably wide-reaching technology?
Yeah, so a lot of things are in the works, especially with machine learning algorithms just taking over the world. InSAR is no different. There are ways in which folks are trying to cut short the time period between actual satellite capturing the image and performance of interferometry and getting the displacement estimates substantially. So right now it can vary between 2 days to 4 or 5 days even. This is going to be instant going forward. A lot of research happening there. And with new satellite imagery now available and planned, that is also going to revolutionize the InSAR space. InSAR, just for folks to know, has been around for a lot longer. And that is being InSAR or SAR satellites are utilized for defense purposes quite a bit. And there are a whole bunch of constellations which are geared towards just the defense aspects. There have been conversations about utilizing that network for commercial purposes. It's been going on for a few years, so I'm not counting on it, but it's going to happen.
Very cool. Thank you. I'll throw another one at you as a fellow digital service provider and consultant. I both love and hate this question, but it comes up every time. And the answer is almost always, it's a huge range and it depends. But I'm sure some people are wondering, can you comment on some costs, maybe specifically for a Deep Foundation application? The one I'm most familiar with is, of course, tracking movement of structures over time. So if there's any kind of boundaries you can put on that, or even just a rough order of magnitude, I'm sure many in the audience would appreciate it.
Yeah, like you said, it's very difficult. But if I have to, the estimates could range between a few tens of thousands of dollars. So 10, 20, well, 10 is probably not the case, but $15,000, $20,000 to $200,000 a year. And I've been part of all those types of projects. The cost aspect is essentially, it comes from first the SAR imagery. If you're using commercial imagery, then there's a cost associated to it. And how frequent do you need the interferometry done and processing done? There have been cases wherein I have reduced the cost by getting all the movement estimates at fortnightly range, but then processing it only every quarter. So those kinds of things can be worked around, but it's a gigantic range.
Yeah, of course. That's a more specific answer than I thought was possible. So that's great. Good. And I hope everyone's taken a screenshot of your contact information here, because JJ is certainly the guy to contact when you're ready to use this tech. But because our intro was so awkward and I didn't have connection, but I do now, can I trouble you, JJ, to go back to the beginning slides with the IMS activities? I'll cover those now and give people just 1 more minute to think of any questions, although your talk was so comprehensive that I won't be surprised if there isn't anything left to ask. Great. So hopefully everyone listening here is familiar with the committees and the communities within DFI, and specifically Information Management Systems Committee, of which JJ and I are members, and hopefully some of you are as well. Or if you're not, this is a great time to join, maybe in time for our next committee meeting, which will be at DFI 49 this October. I hope I got that right, in Aurora, Colorado, in Denver. We do a lot. Thank you, JJ, for that plug of our generic data management specs. We're very proud of those. That's been probably where we've put the most effort on this committee in the past few years. These are specifications based on the U.S. Army Corps of Engineers work, but made generic without U.S. federal language and specific requirements that we don't believe is necessary throughout the industry. So these are free and available for your projects to get high quality data from your Deep Foundations work. And we've had a busy few months. We had a great panel discussion and presentation series at IFC. That was the Equipment Expo this spring in Dallas. And we've also been very active in DFI's work in the Seepage Barrier Summit and Workshop series with the Army Corps of Engineers and lots of members of the industry. And one work product that has come out of this is we're writing a few easily digestible 2-page bulletins specifically on addressing work for the Army Corps of Engineers, and including some lessons learned and recommendations that we on the industry side have for the government to improve those specs. And all of this will be rolled out further and discussed at our next few meetings. Hope to see some of you there. Great. So if there are no further questions, please feel free to contact JJ. Good. Well, thank you all for participating. This was really a high quality webinar. I'm very happy to have been able to facilitate it for you.
Thanks, guys.
Thanks, JJ. Thanks, Jamie.
Thanks, Jamie.